everyone, welcome to today's workshop on Keras 3, a shortcut to master AI. Let's get started. I want to introduce myself. My name is Divya. I'm a software engineer on the Keras team at Google. I'm the technical lead and key maintainer of KerasCV and also a maintainer of Keras Modeling API. So if you haven't already, please sign up with Google Collab. This will take a few minutes. You will need to log in with your Gmail and create an account. By default, you'll get access to GPUs for 8 hours per month with Collab. You'll need that for some of the CV and NLP examples that we'll try out today. And the scripts that we'll be using in today's session is at this GitHub repo. I'll give you a second to make sure you all have access to this repo. If you have any questions through the session, please feel free to ask them on the chat. I have my teammates, Ramesh Sampath and Gabriel Raskin, who'll be helping with answering those for you. So multi-backend Keras is back as Keras 3. So here's why it's special. We brought back framework optionality. That is, Keras 3 now works with any backend of your choice, either TensorFlow, JAX, PyTorch, or NumPy. It is essentially the same API with a reduced size because we got rid of TF1 support. It is no longer tied to TensorFlow backend. It is a drop-in replacement for TF Keras. So any code you already have with Keras 2 will mostly work with Keras 3. So you can set the backend for Keras with the Keras backend environment variable. The backend needs to be set before you import Keras, and that will change how the library are imported. So if you want to or we'll go over the example today in our demo and we'll show you how to do this. Okay, so in today's workshop, we'll explore multi-backend Keras, that is Keras 3.0, how to write a simple model, how to run it with a backend of your choice, including TensorFlow, JAX, or PyTorch, learn deep learning best practices, learn about KerasNLP and KerasCV modules, and how to build some cool AI applications. So these are our Keras mascots. The guides and examples we have online are marked with them to indicate the complexity level. So Keras is a deep learning API written in Python, running on top of auto differentiation libraries like JAX, TensorFlow, and PyTorch. Keras 3 makes it possible to run Keras workflows on top of any backend. So if it enables you to seamlessly integrate Keras components like layers or models or metrics as part of top-level TensorFlow, JAX, or PyTorch workflows. So our goal is to ease this process of building and training your model by offering consistent and simple APIs. So let's talk about the Keras ecosystem. We have the modeling APIs for building your model. We have training APIs for training your model, and we have domain packages designed for computer vision and natural language workflows. So the Keras Modeling API, the goal of having this API is to make defining a model more easy. There are two important concepts here, a Keras layer and a Keras model, and we will look at them now. So the Keras layers API, the layer is like the main building block of Keras models. So you can view them as a model, a model as a graph of nodes, and each node is a layer. So the Keras layer basically has a list of variables attached to it, and it has a forward pass logic. So a layer is a combination of computations that you can reuse, and you can also write your own custom layer with Keras. For example, a transformer layer has a multi-head attention, followed by layer norm, followed by two linear mappings and an activation function. So, and this set of computation happens repeatedly. If you're using that layer in a transformer model, we'll reuse that multiple times. So when you define a custom layer like that, you can use this multiple times. So the Keras Keras layers.layer does auto variable tracking and comes with support on initializers, on constraints, and regularizers. So now we'll move to our first demo. So Let's open the Collab file titled Explore Keras 3, Women in ML 2023 IPYMB file. So we can try this example together. So this is our Collab environment. First, you can choose a runtime type. And for this specific example, CPU is good enough. And if you're running CV or NLP examples, you can choose one of the GPUs. I think you would have access to the T4 GPU. Once we have done that, we can go ahead and install Keras 3. And once Keras 3 is installed, we are going to set the Keras backend variable here. So in Collab, we can do that by using os.environ, set your variable name, that is Keras backend. Here I'm using TensorFlow. You can change this to JAX or Torch and try this example on the backend of your choice. So once we do that, we will import Keras, and we need to set the backend before we import Keras. I just spoke about the Keras layer, so let's see an example. Keras offers various layers, and one of them is dense. So let's try that out. So we initialize the layer, call layer dense, define number of units. We're choosing 2, an activation function. We're using ReLU, and base initializer, we're going to initialize. Bias initializer, we're going to initialize it with zeros. Let's take a random data, and once we have defined our layer, we can just call the layer with your data, and you'll get an output. So that is our output. So here's an example to show how to write your own custom layer. So you would define your class, provide your layer name, and we will subclass Keras layers.layer, and we'll initialize here. So anything you want to initialize during initializing your layer, you define that here. And all the variables that you need tracking during your training of the model, so those will be defined under the build method. Here we have weights and biases. And the call method will have the forward pass logic for your layer. And in this case, it would be inputs multiplied with weights, and the result is added with bias. So once we've defined our custom layer, we can initialize it. We'll provide number of units as 2, and we can call that layer with our data. And there you have it. So let's go back to our presentation. So there are 3 ways to create a Keras model, with a sequential API or a functional API or a subclass model. And let's look at them in detail right now. So here's an example of a sequential model API. The sequential model is appropriate for a plain stack of layers, where each layer has exactly 1 input and 1 output tensor. So the functional API is a way to create models that are more flexible than the sequential API. So the functional API can handle models with nonlinear topology, shared layers, or even multiple inputs and multiple outputs. The main idea is that a deep learning model is usually a directed acyclic graph of layers. So the functional API is a way to build layers, graphs of layers. For more flexibility, you can write your custom model by subclassing Keras.model. And if you're familiar with Torch, this is very similar. So let's try this out in our Collab. So we'll continue in the same Collab that we were using right now. And here's an example of the sequential API. So you define a sequential model by calling Keras sequential, and we just list the set of layers we want to stack one after another. We have input, we have comp 2D, max 2D, flatten, dense, and softmax. And that's it, you have your sequential model. And we can visualize that using sequential model.summary. And that will give you the list of layers, the output shape, and the number of parameters here. And you can call this model with a random input or any input of your choice for that matter. And we get an output from the model right here. So in order to build the same exact model using a functional API, you would do the following. First, we define the inputs. this would be our first layer. And we pass the input to the next layer like so. We define the next layer, pass the previous output as the input to the next layer, and we take the output of that layer, pass it to the next layer, and so on. So we build the same exact model here, and now we have our inputs, the first input that we pass in and outputs from the last layer. And we define the functional model as keras.model, specify your inputs and specify your outputs. And you can again visualize the model that we just built using model.summary, and also call this model on your data. So you can see again the model structure would be same as the one that we just built here. But in order to really show the capabilities of functional API, let's try multiple inputs. We have input 1, we have input 2, we define, and both are Keras input layers. And the next layer will be two conv2D layers that will take the inputs, input 1 and input 2. And in the next layer, we'll combine these outputs, x1 plus x2, and pass it through a max pool 2D layer and a flatten, and then these are plain stack of layers after that, and then softmax. And when you do model.summary here, you will see that we have an additional column here to kind of help you properly visualize what your model looks like. We have our input layers, and then the conv2D layer, you can see that the input it's connected to the first two layers that we defined here, and the max pool 2D layer will basically take the input after adding the two outputs that we have from those two layers. And then it's a stack of layers. You can see that each layer is connected to the previous output, and so on. So we can run that as well. And the third option that I mentioned was subclassing the keras.model. In this case, we'll define class, specify your model name, and we'll subclass it from keras.model. And in our init method, we are going to define all the layers that we will be using for our model. And in the call method, we will define the logic or build the graph, basically. So we'll call the first layer, specify the input, call the second layer, specify the input, and the output is fed to the next layer, and so on. This is also basically what we just saw with the sequential model, how to write the same model with model subclassing. So we can initialize our model, pass the input, and also we can visualize the model in a similar way. So the models are callable. We just saw how to do that. We just initialize the model and then call them on any data that you want. We can also slice the model that we just defined. For example, keras.model. This is a functional model API that we spoke about. So we just take keras.model, specify inputs as the functional model's input layer. That's where it starts, and outputs is the functional model. Take the let's slice it at the conv2D layer, and this is how you do it. So you do functional model get layer, specify where you want to slice your model, and take the output of that layer and pass that. Make that as the final output of your sliced model. And when you summarize, when you do model.summary, you'll see that you've sliced the model and you've just taken the first two layers of the model. So we can go back to our presentation. So we just saw all the three ways we can build a model using Keras, and the key takeaways is by default, go with the functional model, which is clear on graph. And for simple use cases like single input, and it's a plain stack of layers, we'll just go with sequential API. Be good for quick testing. Only use model subclassing when the about to don't fit for your use case, or if you prefer the dot style coding. Okay. Let's move on to the training APIs. So a complete training workflow consists of preparing the training data set, a crucial step in the machine learning workflow. The model, which is the heart of the machine learning workflow. It is a mathematical representation of the relationship between the input data and the output data. So the forward pass is the process of computing the output of the model given an input. The backward pass is the process of computing the gradients of the loss function with respect to the model's weights. So the gradients are used to update the model's weights during training, and logging is the process of recording information about the training process. So Keras provides training components like a number of built-in loss functions, optimizers, metrics, and callbacks. So the loss function is used to measure the difference between the model's predictions and the true labels. The optimizer is used to evaluate the performance of the model during training. The callbacks are used to monitor the training process and take actions based on the monitored values. And Keras provides a number of built-in callbacks. So the training entry point is the model.compile method. It is used to configure the training process. So this includes specifying the optimizers, losses, metrics, training mode to use, XLA, do you want to use XLA or not, etc. And model.fit method is the primary method used to train the Keras model. So it takes a number of arguments which can be used to control the training process, like the input data, the target data, epochs, that is the number of times you want to go over your data set for training, the batch size, that is the size of the batches to use during training, validation data, a tuple of X validation or the input data and the labels for it, and to be used for validation during training, and the callbacks, that is a list of callbacks to be used during training. So let's go back to the Collab and see how to train our model. So for now, I'm defining a random training data. For data, I'm just defining a randomly initialized input that is of batch size 20. And we'll also create labels for the corresponding data. Now let's use a functional model that we defined above, and let's see how to compile and fit this method. So we've initialized the model. Now model.compile will specify the loss function and specify the optimizer. The loss function we are using here is sparse, excuse me, sparse categorical entropy, cross entropy. And for optimizer, we're using Adam. And for metrics, we're using sparse categorical accuracy metric. Excuse me. So once we have compiled our model, we'll do model.fit with a layer, a data and label which is defined above. Excuse me. So once we have trained our model, we can save them and load them. You use model.save weights, and we save our model and we load weights back using model.load weights and your file name. Excuse me. So I want to talk about building custom components and layers in Keras. This is a significant enhancement in Keras where the creation of custom components and layers is streamlined through the standardized set of Keras operations. So the Keras Ops API basically ensures compatibility and implementation across all supported backends. So another exciting thing or enhancement that we have for Keras is the Unified Distribution API. So the Keras Distribution API is a new interface designed to facilitate distributed deep learning across a variety of backends like JAX, TensorFlow, and PyTorch. This powerful API introduces a suite of tools enabling data and model parallelism, allowing for efficient scaling of deep learning models on multiple accelerators and hosts. Whether you are leveraging the power of GPUs or TPUs, the API provides a streamlined approach to initialize distributed environments, defining device meshes, and orchestrating the layout of tensors across computational resources. So let's look into this more in detail. So there's various ways to take advantage of multiple accelerators, and the most common one are data and model parallelism. So you should be free to choose any distribution strategy without changing the underlying model structure. So what do you mean by data parallelism is the model weights are replicated across all devices and each device possesses a portion of the batch data. Model parallelism will be mostly useful when model weights are too large to fit in a single accelerator. So this allows you to split your model weights or activation tensors across all the devices on the device mesh and enable the horizontal scaling for larger models. So I have an example here that demonstrates how to use Keras distribution API using device mesh and layout map. So the device mesh here represents a cluster of computation devices configured for distributed computation. So here we define a 2x4 device mesh with data and model parallel access. Then we create a layout map from the mesh we just defined. And the layout map will let you specify the tensor layout for any weights and intermediate tensors from global perspective. So this code here means that any weights that match with D1/kernel, it will be sharded with model dimensions, that is 4 devices. Same for D1 bias. All the other weights will be fully replicated. So once we have that, we can set the distribution. And any code you write below this will be sharded according to the settings we just specified. So it is also easy to change the mesh structure to tune the computation between more data parallel and model parallel. You can do this by just adjusting the shape of the mesh. We have 2x4, we can change that to whatever you like. And no changes would be necessary in your code or model that you define below this. So Keras applications are deep learning models that are made available alongside pre-trained weights. So these models can be used for prediction, feature extraction, and fine-tuning. So we offer a long list of models, various versions of them trained on various data sets, and are directly available through Keras applications that you can instantiate with like one line of code and play around with them. So do check it out. So in the last few years, ML innovations have greatly expanded our understanding of what is possible with machine learning, from breakthrough performance in classic benchmarks to exciting new field of generative AI. It's critical to stay up to date with the latest models to be competitive. So at the same time, state-of-the-art models have gotten increasingly complicated and often require expensive pre-training to be useful. This is where KerasCV and KerasNLP steps in. That is it is the easiest way to deploy state-of-the-art pre-trained models for text and image classification, object detection, generative AI, and more. So with these libraries, you'll have access to cutting-edge models with a simple and consistent API. So KerasCV is a library of modular computer vision components that work natively with TensorFlow, JAX, or PyTorch. It is integrated with Keras 3. It offers over 35 augmentation layers, pre-processing layers, pre-trained models, metrics, and bounding box utilities, and more. So any model on KerasCV, you'll be able to run on a backend of your choice. So let's check it out. Let's check out what we can do with KerasCV. So let's start with image classification. In this example, we would like to classify images as cat, a negative label, or dogs, a positive label. So the highest level model in KerasCV or NLP is a task model. So a task like image classifier is a Keras model consisting of a backbone submodel and task-specific layers required for solving a specific problem. So backbone models in turn are a set of reusable layers, generally pre-trained on separate tasks to extract highly informative features from the input data. That would greatly reduce the amount of labeled data and compute resources required to get competitive performance on your task. So in this workshop, I'll go over a few things we can try with KerasCV and NLP, and we can try out a few examples on the Collab demo. So for object detection, KerasCV offers this is a more significantly complex task than image classification because the model can detect any number of objects and must predict a class and bounding box for each. So in this example, the blue box and classes are ground truth labels for objects in the image, and the orange boxes are classes that are inferred by the KerasCV retina-net model. So despite this added complexity compared to image classification, creating an object detection model with the retina-net architecture is very similar to how we do image classification. We also offer semantic segmentation. It is a type of computer vision task that involves assigning a class label such as person or bike or background to each individual pixel of an image, effectively dividing the image into regions that correspond to different object classes or categories. Image generation. Exciting, right? So KerasCV provides dead simple interfaces to the latest text-to-image models such as Stable Diffusion to generate novel images from your text prompts. So you would simply instantiate a Stable Diffusion task with the desired output image size and then call model's text-to-image method with a prompt and number of output images. So let's try this together. The notebook file titled Explore KerasCV Feminine ML 2023. So I have already run this Collab, so I'll just go with the outputs here because we do not have time to wait for the Collab to run. So the first block here basically installs all the libraries that we need today. It's a little bit more complicated, looks a little bit more complicated today, but this will be simplified soon. You can pick a backend of your choice here and try to choose something else that you didn't try in the previous Collab and and hit run. And once we set our backend, we will assign that backend using OS environ, set your Keras backend to whatever you choose, and let's import Keras. So in order to just make sure what version of Keras you're using and what backend you're using, just you'd run this block and see that we're using Keras 3.0 and it's running on right now TensorFlow. Whatever you set here, it should show the same backend here. So let's move on to trying out Stable Diffusion with KerasCV. You would instantiate the Stable Diffusion model using KerasCV models, Stable Diffusion, and your model is instantiated. Also, JIT compile is enabled by default for Jackson TensorFlow. That is your model runs faster, but it is right now disabled for Torch and it is a work in progress and will be added soon. Now let's try out a fun prompt. I have the prompt that says a refined pencil sketch of a machine learning developer. Feel free to change this up to whatever you want. And we will use Stable Diffusion text to image method and provide our prompt here and specify how many outputs do we want here as batch size. I'm going to use 3. And let's take a look. And it's going to generate the images and we'll plot these images and see how that looks. So for the prompt that I have here, pencil sketch of a machine learning developer, using TensorFlow, we have the following output. I would like to see if you guys try out some fun prompts to send it. I would love to see it, something fun. So now let's go back to our slides. So we're constantly adding more generative AI capabilities to KerasCV. And here are some advanced features we already support. Textual inversion is a method to teach stable diffusion models specific visual concepts via examples. For example, we can provide a set of input images to teach the model about our teammate's cat and then ask for it to be visualized as a fantasy character. So, and we also have prompt to prompt. It's a method to modify the prompt to stable diffusion while keeping the image visually consistent. For example, after asking stable diffusion to generate a photo of a dog with sunglasses, we can replace dog with cat and get a visually similar image of a cat wearing sunglasses instead. If you want to learn more, check out our generative AI guides on Keras.io. So the next exciting thing that we have is a text prompted segment anything model. A segment anything model is a new AI model from Meta. It can cut out any object in an image with a simple click. And KerasCV offers segment anything model as well as grounding dyno, which allows you to use a text prompt to select a box with which the segment anything model segments the object. So let's check out how this is done. So I'm going to go back to my Collab here. So for the segment anything model, we are going to call the grounding dyno model here. And we're going to download the grounding dyno model weights here. And we have a bunch of helper functions to visualize the masks and boxes. So just go ahead and run those. So for our grounding dyno model, I'm going to download the config and weights and initialize my grounding dyno model. And we have our sample input of a cute dog hiking. So we are just going to get that image and visualize it in this block here. And coming to the exciting part, let's try out the text prompted segment anything. So the first step is to use the grounding dyno model and use the function predict with caption. And we input our images, and this would be our prompt. So in this image, what do you want to segment? And let's try to segment the harness of the dog. So once we provide those inputs, the boxes that has the object is predicted by the grounding dyno model. And that box is, let's have that box for now. So we're going to initialize the segment anything model using KerasCV models, segment anything from preset. So we're going to use a preset that's been trained on SA1B dataset. It is trained for a huge segment anything model. And once we've initialized our model, let's go ahead and compile. And once we have compiled our model, we will use model.predict, pass the image of our dog, and the box that we just predicted using the grounding dyno model here. So once we specify that, we have our output, and our output contains the mask. And let's go ahead and visualize the mask that we just predicted. So we have our dog, and this is the harness of the dog. So I know this is a two-step process at the moment, but the team is working on adding clip to segment anything model that will allow you to just provide a text prompt and have an output image of the segmented object that you just specified. Okay, so let's go back to our slides. All right, so just like the examples we just saw, where we use the presets. Now KerasCV offers several other models and presets that you can use off the shelf. So make sure you explore them. So moving on, KerasNLP is a natural language processing library that works natively with TensorFlow, JAX, and PyTorch. It's also integrated with Keras 3. It offers building blocks so that you can write your custom workflows with less effort, like layers, tokenizers, pre-processing layers, metrics, etc. So let's check out what we can do with KerasNLP. So we instantiate a BERT classifier task model using the from preset constructor. One difference from KerasCV is that KerasNLP task models like BERT classifiers include pre-processing by default. So this means that you can pass raw strings at both training and serving time without worrying about the correct tokenization and packaging methods. For this reason, it is best to call from preset on the task model itself rather than passing an explicit backbone. So this will automatically give you a matching preprocessor class, which will tokenize and pad your input text to match the expectations of the backbone class. So in this case, we will use BERT-based English uncased preset. And this backbone has been trained on gigabytes of text data to understand the meaning of words in context and extract more information from our labeled examples. You can find a list of all available presets in the class docstring or on the Keras.io website. Then we do model.compile and fit. Then we use the model predict to perform inference. So the input is basically 2 strings of movie reviews, and the output consists of scores for negative and positive review. And we can see that the first one is classified as positive. What an Amazing Movie is classified as positive, and the second one is classified as negative. Okay. So the next thing we can do is text generation. KerasNLP offers text generation using popular models like GPT-2 and OPT. Causal LLM is a task model that predicts each token in an input sequence given all the preceding tokens. So it is a canonical approach to training generative text models that can predict new tokens given a user prompt. So let's try this out. For this, we'll be using the third notebook I have in the repo that is titled Explore KerasNLP Women in ML 2023 IPYMB. So I've already run this Collab and I will go over it with you and you can try it along with me. So first thing is we'll install all the packages that we need and we will select the backend. So we've tried TensorFlow and JAX, we can try Torch this time. And then we import Keras and then we check what, okay, I was using JAX here. All right, so we can check the Keras version and what backend you're running. And let's check out a generative model and build like a chatbot using OPT Causal. OPT is a causal language model. It continues the input prompt. So I'm setting a random seed to make sure that I get the same output every time. So we initialize the model using KerasNLP models, OPT Causal LLM from preset. I'm using OPT. So this is basically a 12-layer OPT model where case is maintained and it's trained on corpus, common crawl, pylon, push shift, IO corpora. So once we have initialized our model, we'll do model.compile and specify our sampler here. And this is basically going to download the weights and your model would be ready for generating some prompts here. So let's try out a prompt. It says, hi, I am whatever backend you're using. Let's say JAX. I'm a JAX machine learning developer. What are you working on? This is the prompt that we provide to our model. and we use NLP model that we just initialized here. .generate, provide the prompt, provide maximum length of the output that you want, and and the response will contain both our prompt and the predicted output. So we'll remove our prompt from it and then check out what the model predicted. So the model responds with a lot of things. I'm working on a couple of projects at the moment. So basically that's the response from your bot. So you were able to build a chatbot with just like 2 lines of code. Next, we're going to try to do fine tuning. It's the same thing we can try with a different model here, KerasNLP models, GPT-2, causal LLM. From preset, we're going to use a small pre-trained language model, 24-layer GPT-2 model where case is maintained, trained on web text. So we'll define our optimizer, and we'll exclude the layer norm and bias terms from the weight decay that we just defined here. We'll compile the model, specify the loss function, optimizers, weighted metrics, and samplers. And we can visualize the model using model.summary. And let's download a data set in an open source. Basically, Databricks Dolly 15K is an open source data set that contains 15,000 human-generated prompt response pairs. So let's prepare our data to train our model, and we can just use model, specify your data, batch size equals 2 and epoch equals 1. So we can go ahead and provide this input to our model and then see what it generates. So model.generate, provide your prompt here, and the model generates basically this response. So the prompt we provided was, what is a machine learning? What is machine learning? And the model responds with, machine learning is used to learn a large amount of data and make recommendations based on this data, and so on and so forth. So you can try it with multiple prompts. So you just learned how to create your own model, and how to use the presets, and also how to fine tune it and customize it for your use case. So just like the examples we just saw now, KerasNLP offers several other models and presets that you can use off the shelf. So make sure to explore them. I've added some links here for the GitHub repos and our Keras.io page. You'll be able to find documentation, guides, and hundreds of examples here. So do check it out. If you're interested in contributing to Keras, which is great, open a PR to get started. Also, our team is hiring. If you're interested, submit your resume online on Google Jobs page. Cool. So yeah. Thank you for joining this workshop today. I hope you enjoy the rest of the sessions at Women in ML Symposium.